So we'll have a few more people trickle in, the post-lunch crowd. Thanks everyone for joining as we hit the last leg of this conference. Hopefully I can entertain you with a little bit of comparing containerized versus a VM-based Cloud Foundry. Otherwise, if you hit a food coma and you snooze a little bit, just don't snore. So, bit of the agenda, what I'm going to talk about today. First of all, I'm going to give a little background on the various technologies that we're going to be playing, was playing with to get to these numbers. Talk a little bit about how we got there, and then we'll come to see the numbers, and talk a little bit about what's next from the experience that was born out of that effort. So first of all, some of you, I'm impatient. I need to get out. I've got a plane to catch. So you want to see the numbers. Well, the entire summary of the next half hour or so comes down to this. OpenStack takes you 33 VMs, 216 gigabytes, and will result in the performance of an application of 600 requests per second. And on Kubernetes, you'll do the same with 42 pods, 34 gigabytes of memory, and get slightly better performance. So if you only wanted the numbers, that's it. You can go now. So first off, what is it that we're playing with here, and why is it a good example? The workload that we're talking about running over OpenStack and running over Kubernetes is Cloud Foundry. Anyone actually familiar with Cloud Foundry? A few. How many people actually running some form of Cloud Foundry? Okay, so it's the same. So it's platform as a service. What does platform as a service mean? It's a cloud-native application platform, a lot of enhanced features that supports basically enriched development and deployment. It is the developer user experience on top of whatever else you may already be using. I hear a lot, Kubernetes, that's for application deployment or development. That's not true if you've actually seen systems like this that are for application and targeted towards the developers, although they really are meant for operators to run, and it's a platform. Why is that? Okay, integrated routing with advanced route handling. This is even beyond some of the things you're seeing in Istio, which itself is still at a 0.x version. Consolidated logging for both system and application levels. Enhanced role-based access control. It has a very interesting org and space model, so users don't actually manage applications. Space and organizations do. Service integration for applications, and of course the whole integrated scaling support for blue-green canary application deployments and more. Originally open sourced by VMware in 2011. This is relevant for a couple of reasons. One, nobody had ever heard of Kubernetes in 2011, much less played a lot with containers. So that's the heritage of the system, and that's why a lot of the efforts have all been on VM-based deployments. Find more about that at the link there. And of course, if you're going to have anything come out of VMware, it's obviously going to want you to consume as many VMs as possible. A little bit about the high-level architecture. So in basically what I'm going to be describing is taking something at the level of Cloud Foundry, and you can kind of see what's here. I'll have a few other pictures to describe a little bit more the complexity of the architecture, but we're not talking a simple application. We're talking something with a lot of stateful information, services, there's database components in there, you'll get console and etcd in there at various points, and then applications that run on top. And it happens to run applications in containers. That's just an aspect of the system. From the user's point of view, it just runs stuff. It has the routing layer at the top, authentication, which I mentioned, and then there's the things which deal with application lifecycle, blob store, container registry, all for storing these things locally, scheduling, the platform services part, And then you have the entire messaging and logging layer, which permeates throughout. So that runs on every single component, giving you metrics and logs for that system. And of course, it runs pretty much anywhere. Here we're talking about the OpenStack infrastructure as a comparison. Well, let's look a little bit at the internals. It's probably a bit of an eye chart. And yeah, that's the way it is, but this is a little bit better view of what we're talking about and the various particular integration of the components that you have at various parts. There's not too much to say here except that you'll see that most of these pieces will wrap up, and when I'm looking at this, it's almost a rough approximation of the various VM breakdown that you'll have of pieces. Just that some of them, the ones that you see, there's a couple of singletons, but the ones that you see that stack, that represents the pieces that you would generally scale more in an environment versus others to get HA. Breaking it down into something that really, this is actually the pieces as they break down into actual components of the system, logically speaking, or rather role-based speaking, these are the pieces. So you have from logging to Elastic Runtime on the other side. The Elastic Runtime is the most important part for scaling, although you'll scale all the various pieces individually for proper high availability setup. There is an internal storage component, so it's very important that whatever you're building this on top of has some stateful storage. There's the services in terms of, these are services that are actually offered to the applications. You can have your own persistent storage at the application level. And then there's things like the internal secret generation. There's the MySQL proxy, because MySQL is the database used. You could use Postgres. In this particular example, on both cases, it's MySQL. NATS is the messaging bus. And then you have your Diego scheduling, various API management, and the routing and access layer. So that was Cloud Foundry. That's the workload that is being used here in comparison. So what is BOSH? For those who have been running Cloud Foundry up until recently, this was the primary tool for deployment. And it's a project, it's meant to unify release engineering, deployment, and lifecycle management of the software. Again, this started to be written several years ago, so it comes from a heritage where, well, I didn't have things like Kubernetes. You might have had Chef or Puppet, but that was the state of the art at the time in terms of deployment software. And of course, VMs is the only thing I had for my role containment. And so that's what I used, VM-oriented deployments. And from that, it of course then naturally, as some behemoths, they grow, that handles monitoring, failure recovery, software updates. It basically tries to wrap the whole enchilada. And it was originally developed for Cloud Foundry, but it has become a general purpose tool. So it is well suited for large distributed systems, which is to say it itself is a large distributed system and sometimes bigger than the workloads it deploys. It has a cloud provider interface with targets for most of the major infrastructure stacks, Azure and OpenStack and VMware, etc. Find more about that, go to bosh.io. So what does it take to install Cloud Foundry with BOSH on OpenStack? BOSH requires a custom base image, a stem cell. This is essentially a generic image with a BOSH agent in it. So BOSH does operate in an agent-based model. And you start with deploying that particular piece to your OpenStack setup, and then you create your usual key pairs. There's the custom security groups, etc. But once you have the prerequisites done, it's pretty much it's its own command here. And you take a particular deployment. A deployment will represent a particular version of Cloud Foundry, sometimes with a few particular options related. And in the particular one that we're deploying, it's a standard high availability setup, pretty much a stock CF deployment for high availability. And you run this, and then there's the BOSH VMs. It's kind of like kube control get pods for those of you familiar with Kubernetes, and it'll run until you determine the ready state. A couple of links there. Basically, from those two links, there's the full set of docs on how you would do the install with BOSH. So what does that architecture look like specific to OpenStack? This is actually taken from Pivotal, from their reference architecture for PCF as OpenStack as one of their target deployments. You have you basically have your floating IP, you put your virtual router in front. You will break things into availability zones. In the particular example that we'll have, it's just 2 availability zones that we've created. And then there's a lot of extra stuff around the side, just for BOSH to manage a whole bunch of stuff around lifecycle and support of updates and similar stuff. Then there's the service tiles. Service tiles will relate to services that you bring into the system to make available to other applications. Most commonly, things like the persistent storage or MySQL available again to the applications you're hosting on top. And then you have to have a load balancing component, it could be Octavia in the particular case of OpenStack, and some sort of blob store available to you. So all of those are the components being leveraged in this particular case. This is an actual picture taken from the particular deployment that was set up, and if someone's curious later, it's still running. So right in the center, though, is basically the Go router, the router functionality, splitting off into what's the 2 main blobs are the 2 AZs that we have set up in this OpenStack configuration. And in each of those AZs, you'll have the Diego, which is the execution runtime component. It'll have a brain component and everything needed to basically have that general high availability for the runtime of the apps. Certain things exist off on the side that in this particular case, they don't need to be fully HA, because if they go down, your apps will still continue to run and you'll still be able to route to them, but you might not be able to do a scaling event or something like that. So don't need to go over Kubernetes, right? That's pretty clear. Now, one of the interesting things is that if a lot of people probably hadn't heard of BOSH, Kubernetes is actually a younger technology, obviously become more popular over time. And you'll note that some of the things that I mentioned in BOSH, things like lifecycle management, are very much absorbed by Kubernetes. Yet here you have this big overlap. So you might say it's already not quite the fair race, but we are talking about different heritage technologies started at different times. And part of obviously my end result, as I showed you the numbers in the beginning, it's always good to take a rethink on your architecture, even at something as large of a scale as a Cloud Foundry platform, to really ask yourself, is it time to rebuild some of the base? Some people are not as familiar with Helm. So Helm is basically the de facto package manager for Kubernetes. Helm.sh is where you'll find a lot of the information. So it manages that discovery and the definition of packages. And those packages can be one or more applications and services, and their deployment and upgrade. So it's a bit about the lifecycle management. It doesn't have any of the scheduling. That, of course, is all related to Kubernetes. And so it takes what you would say with BOSH. It has 4 major functions. The Helm addresses the release engineering part, not the rest. So similarly, we're going to, in comparison, the SUSE Cloud Foundry is an effort. It's open source that for reconfiguring Cloud Foundry for running in containers. It deploys via Helm. And it's a two-step process rather than a one-step process. It's actually still much shorter overall, but you install UAA. I think I mentioned that's the authentication component. The reason you install it separately is you can have one user auth component for many Cloud Foundries that you might have in a Kubernetes cluster. You wait till it becomes ready, then you go ahead and Helm install your Cloud Foundry. And so it seems simple, then you're done. But first, let's take a step back, because, all right, so I've just shown those the two comparative, that's how you get to these two systems that were built. But how did we get here? You know, how did we go from VMs to containers? So in containerizing Cloud Foundry, I mentioned before, it's basically relied on BOSH for its deployments. BOSH relies on VMs. It is all a heritage choice. I don't very much think that people would redo it in that way if they were to start again today. In fact, there are some efforts, in addition to this one, there are other related efforts for containerizing in Cloud Foundry and BOSH specifically, because, again, BOSH has become its own general purpose system unto itself. So when I say we wanted Kubernetes, this is SUSE. We're of the opinion that when you look at Kubernetes, it's becoming kind of the de facto base layer for a lot of enterprises. You might not be running it, but you're probably playing around with it. And in much the same way, of course, we have our own OpenStack distro. We also have our own Kubernetes distro. But when we're looking at the application deployment side and the application user experience, we see that that's happening a lot more around in the Kubernetes space, which still hasn't really solved ease of use application deployment. And so that's what we want to bring Cloud Foundry to. So, enter Fissile. Fissile is about converting BOSH manifests into containers. Go into a little bit more what that actually means. And for us, the only key requirement was maintaining Cloud Foundry certification, because just much like there's certification on many of these things, when you want to make a distribution, you want to at least get that stamp of official approval from upstream that, yep, these guys are consistent. So that meant that we had to bring in essentially the Kubernetes awareness. Now, I will say that we're really at a V1 stage with Fissile. So I mentioned that BOSH has a few different pieces. One of the main pieces is release engineering, and the release engineering basically creates, as I said, the BOSH manifests. BOSH manifests define all of those roles that you saw before. They basically say, hey, this is the software that goes here, and this is all the dependencies that build each particular role, encapsulated at least to that level of role. So Diego, the brain, with what the brain is doing with talking to a message bus and thinking about some container scheduling stuff. Then there's the Cloud Controller API. It's a Ruby application that is what you talk to when you want to make command and control changes to the system. And so it thinks about all the dependencies it needs at the Ruby level, talking to MySQL, talking to Nats, and then everything else is at the API level. So when we're looking at this, we're taking that level of a definition and trying to bring some Kubernetes awareness to it. At the services level, this means basically proper logical grouping of what is roles into Kubernetes pods and bringing the right routable entry points into it. Stateful sets, we want to make sure they're restricted in use as much as possible, but they absolutely do exist in the system, and they pretty much have been focused to go around the core controller data. I can say a real pain in the butt that we had at one point was trying to get console, which was part of the Cloud Foundry ecosystem, all very well behaved, and even when you get through for Helm upgrades and things like that. And that was fortunately removed from the ecosystem, made our life much easier around stateful sets. And then there's the liveness and readiness probes. So we're moving from a VM-based system that uses Monet, which is kind of a standard, process monitor that does particular actions, and we haven't completely gotten rid of it. We've instead wrapped liveness and readiness probes in Kubernetes. The difference between, hey, I'm still alive, so you don't need to restart me, to the readiness being, not only am I alive, I'm actually ready to take data, and change those from the basic VM assumptions to container pod ready. So, what's in a container? You basically start from an OpenSUSE Leap container. I mentioned that there's the stem cells. They have a little bit of BOSH agent awareness. They also add a little bit of extra Cloud Foundry specific pieces. So we are not getting rid of those pieces. So here we're looking again at that bottom piece will all be a container. And so you'll see we add packages and jobs plural. At this time, we're still dealing with multiple processes per container. We're writing an entry point. There's a little bit of tooling for the configuration. And again, we're leveraging the exact same BOSH releases that define VMs. So we're creating what you would often kind of think is, it's a bit of the lift and shift of the VM to containers. But there's a little bit of extra knowledge in there that comes in with config-in and some secret sauce that it's not so secret, it's all open source, but you find where we're basically adding a little bit of sauce in there saying, okay, you were in a VM, but now you're in a container to behave a little bit differently around the entry points. And basically that becomes an assembly line. That's the entire purpose of Fissile, is to say, you're not for VMs, you're going to be for containers. So we take that role manifest, we take some of the opinions. The opinions are configuration information, take it from the BOSH releases, and out come container images. Then the next bit is, so mention the opinions and all these opinionated defaults. It's a system that really has many opinions. We're talking 500 different things that you might touch in the VM-based system. There's really kind of thousands of them. Most of them are sort of duplicates of each other, but just spread across a whole bunch of different YAML files. And you kind of have the same thing here, but we basically want to shield the operator from that complexity. So at its minimum, you need to change only 3 variables in the Helm file when you're going to push something. You basically need to have an IP, you need to have a name for that IP, and you need to say kind of where you're pushing, and then it gets into things like sizing. The nice thing about Helm is that we can actually make very simple declarative commands. One is, it's not showing in this one, but there's one that says HA, true or false. And just by changing that, you can go from a basic configuration to a highly available one. And the Helm will take all of the necessary work to increase the size counts for the important pieces to go and be HA. In doing all that, what have we achieved? So we can horizontally scale to make sure all user applications suffer no downtime. And basically, we can survive the chaos monkey in this system, which is the very important aspect when you're trying to build platforms. So you saw the architecture on OpenStack. This one's actually ours, drawn by us. Maybe we just need to get a little cleaner. It's definitely an eye chart, but this is the actual, Kubernetes where things are talking to. The Kubernetes boundary is actually that outer border. User network here off on the right side, and particular third-party services that may exist also around the outside. So each of those being a particular pod, and then the pod communication being the arrows. You will see that There's a box within a box over there, and as part of the Cloud Foundry certification, there is the Diego container runtime. So it has its own sort of container scheduling system. Yes, we happen to be running on a system that does scheduling itself, but at the moment we still need to keep this piece in there to be a Cloud Foundry certified. What does that look in the end here? We'll take away the eye chart and get to the architecture level. So SUSE Cloud Application Platform. This is something that is containerized. You have the various pieces, and it's meant to just run on any Kubernetes. Again, this is the philosophy that eventually Kubernetes will become a pretty much standard in the data center, or as it's already becoming in the public cloud. You can download and run this on AKS, EKS, or GKE today. So back to the numbers. The OpenStack Cloud Foundry deployment happens to be running on OpenStack Cloud 7. The numbers that we're looking at, it's less important in terms of the performance of the system. Yes, they're DL360 Gen 9 servers, than it is on just the overall particular aspect of bloat. So we're talking mostly about bloat here. And the number is as snapped right from the console. We basically created a project just for the BOSH deployment and did a standard HA BOSH deploy. That generated the topology that you saw earlier. That takes 33 active instances and 216 gigabytes of memory. And it also takes about 94 minutes to come to ready state from cold. Cold being we have none of the sources local to the environment that this was being run in. And it's not the fastest internet. So actually a ton of that time is download time. In terms of the rest of the pieces, you can see here 51 vCPUs, there's some floating IPs being used and volumes. The volume storage. It says if you look up, hey, what are the OpenStack requirements for running this? It says having 1 terabyte of disk. You can see it's actually not using nearly that. But these particular deployments were only set up. They are pretty base case and only had 2 different applications deployed on them. Both of them simple Go applications. So it's not like we're using them in anger in that sense. So a little bit about the CF instances. This is just a small snapshot. You see there were 33 in there. A couple that things just want to highlight from here is that there's, and this is not an uncommon design pattern, but the top one you see there is a jump box. So you always have to then, oh look, you've wasted 8 gigs of memory on a 4 CPU machine just to have a jump box to talk to the rest of the system, because you're not able to rely on existing underlying platform setup for whatever it is, like a kube control directly from my Mac into the system, or being able to do a Helm locally, etc. So there's little aspects of that bloat that spills over. BOSH itself is the next line there, 16 gigs, and there's a couple of other BOSH VMs. So just to maintain this BOSH subsystem, which is doing a little bit of the release engineering, lifecycle management and such, you're also losing some of that extra overhead. And then we'll just sort of jump to the last line on the screen is the Diego cell. As I mentioned, this is where the containers are running for the Cloud Foundry platform itself. In OpenStack, we'll just assume a raw OpenStack, ignore Magnum or anything else running. Obviously, it has to create something for it to be scheduling containers onto. In this particular case, it's a 30 gig VM, and I've, of course, only pushed, I think, 256 megs worth of app usage. So, there's all that extra provisioning that you have around it in a VM model that ends up representing bloat. And obviously, you know, it's not containers. It's not a lot of sharing going on here. And yes, you may over-provision your system somewhat as you do in the VM space, but that's an awful lot extra when we compare it 216 to 34. So, the Kubernetes deployment. It's running on bare metal, a bare metal Kubernetes install, same hardware. SUSE, it happens to be SUSE CASP v2, just for reference. It's Kubernetes 1.8 with an NFS-backed persistent storage. Again, the number of pods this ends up being is 42. And the memory reserved, which is slightly different than the memory. The memory you see here from the snapshot is actually from Heapster, so it's showing current memory usage, not the reserved limits, is 34 gigs. Now this is the same level of high availability between these two systems. So if you're thinking about from pure functionality perspective, I'm getting exactly the same Cloud Foundry experience, the exact same, you know, user development, deploy, push, the ability to create extra services, the ability to bind those services to my applications. Nothing there is different in either of these. In fact, the end user wouldn't know where one or the other might be running, except that they're different endpoints. This effort is really all about the operator and the fact that the operator does actually have to be concerned at some point about how big their production systems are going to get. And actually, it's not even always about the production system. One thing that we hear a lot is, you know, those that are running in production and, oh, I've got a lot of money. I'm a big enterprise. I've got a lot of money to throw at production. I don't have any money to throw at dev and test. And so, you know, they're always cobbling together smaller amounts of hardware, and you can't spend 200 gigs just to run a simple dev cluster. So don't waste that much space. In terms of the deployment time, so before that 94 minutes, that was the BOSH deploy step. This is the Helm install step, and this one we did do twice in this particular state. So it was 60 minutes to ready state from cold being no cached sources. One thing that the Helm is doing is pulling things into a local Docker registry. So once everything is primed and you haven't changed that, and you don't worry about the download speed from wherever your Docker registry happens to be running, it is pretty quick, 6 minutes. The same would be true for the OpenStack deployment. We just didn't go through a warm deploy. So when it comes to the number, a basic app routing request, this is just an Apache benchmark. It's against a simple Go application, and it's goenv. It's one of the very simple standard Go test apps for Cloud Foundry. In each case, there's 2 app instances and 2 routers in each environment, and we're running 10 concurrent requests consistently over a 2-minute time period. And you know, you can Apache bench all the gazillion configuration variables you want, but it comes out to about 600 requests per second on OpenStack and 664 on Kubernetes. Again, there's nothing from the user's point of view except that I was able to deploy my app, so it's nice to see, oh look, I get a little bit more performance out of one system than the other. Again, all other things being equal in terms of hardware. But you say, what about, okay, let's talk about a few of the things that you know, maybe not comparatively apples and oranges here. So yeah, it's not apples and oranges. It's not the same kind of apple. You know, you pick your red or your golden delicious there, but you are getting the same experience, as I mentioned before. From the user's point of view, there's absolutely no difference between these two systems. There is a huge difference from the operator's point of view. Now, if you don't run Kubernetes, that's an entirely different beast. So when I talk about things like core system resources and such, yeah, it's fair to say that if you're very familiar with OpenStack and not at all familiar with Kubernetes, then there's there's a huge effort because the two things do administer differently, they do get maintained differently, and you have to ramp up on that. But otherwise, that is the operator experience. And I was going through as someone says, well, oh, but you've got OpenStack. The layer of turtles you have from OpenStack to Cloud Foundry is increased because you've got your virtualization and the hypervisor, and Kubernetes is running at the bare metal. And I'm like, yeah, that's an advantage. That's not a difference in the system. Sure, there will be people argue, well, the hypervisor will give you certain particular advantages, but it's becoming increasingly more common that people are actually getting really good at just doing bare metal Kubernetes installs. And if that's the case, then try and go as low as you can to remove those extra layers of indirection. In fact, because everything else is equal, because these are the same versions of Cloud Foundry that were being deployed, really the only difference, the only reason I got 10% better in one system or the other is I removed a networking layer. And good, that is possible. I will say though that there was overcalculation in some of the extra reserved roles. I mentioned that the Diego cell, I forgot to bring it up. So the Diego cell was 30 gigs in the VM, and it's actually showing here. It's showing us the last line on this one. It's showing us 7 used, but actually they're 8 gig cells in the Kubernetes deployment. So 2 times whatever minus 16 gives you, okay, there were 34 extra gigs of space wasted. Unfortunately, in this particular design of the system, you can't make that choice. You can't, you can add and remove Diego cells over time, but the basic, unit in BOSH deployments is 30 gig Diego cells. They say, they specifically talk about, hey, make these flavors available, and I'm going to use these flavors. Yes, you could go hacking deep into the vars and say, use smaller ones, and then I'll create them as I need them more quickly. But that's basically affecting, working to the lowest common denominator aspect of the system, rather than leveraging directly what you want to use. So what's next? Okay. Here we are, we've come, there's those two systems. I mentioned it's a bit VM lift and shift at this point with some extra sauce around it. There are two, there's another slide related to this, but there's two very important pieces that we're currently working on with IBM and SAP as we continue to improve this refactoring of Cloud Foundry. The first is, I mentioned Fissile is basically the next generation of Fissile. One, it's bringing more Kubernetes native awareness. The entire point is more Kubernetes native awareness to Cloud Foundry. And I will say, some people say, well, you're containerizing or something like that. In this specific work effort, we're not containerizing, we're cubifying. We are doing work that is specifically to the architecture, the pod specs, and Kubernetes terminology. You would do something different if you were to take it to Mesos or Docker Swarm. So we're cubifying further. The most important aspect of that, and kind of the most of the work involved here, is, so as I mentioned before, all of those roles are defined in multi-jobs that fit into a unit. And of course, the units before has always been VMs, and there was never any reason to subdivide it further. But the ideal is one process per container, and the concept of pods is that, well, you can actually have multiple containers in a pod. We are really mostly except for just a couple of cases where we're a little more advanced here, is we're pretty much running one container per pod, but that container is running multiple processes. So we need to get to a finer grained definition of these components so that you can actually do better pod management. And from that, so that's basically working with the BOSH team upstream. It's called BPM, BOSH Process Management. And instead of defining things at a role level, it defines them at a finer job level. And then work on the automation of that to get the pod specs out. And we'll just sort of magically be able to take, again, those same upstream manifests, which will just be finer grained, and where they'll co-locate various things onto one VM, we'll subdivide them into single containers, multiple containers per pod. The other is finally to just get rid of Monet. It actually has improved upstream so that Monet is mostly not used for any of its special features, but there are still a couple of roles where they have some special case things they do with Monet. We want to get rid of that so that, or at least abstract it so that we don't have to have Monet in the Kubernetes case, but you will of course need it or something like it in the VM situation. The second piece is Project Irini, and that's basically replacing that Cloud Foundry scheduler with Kubernetes native deployment. So this will get rid of that whole Diego cell overhead. There is an example of this already working. The idea is basically you can improve density, consistent networking, etc. And running out of time, so there's a few more things. Istio is already being worked into Core Cloud Foundry. There's a Kube CPI for BOSH also being developed that sort of fits in and builds all these things together, as well as work around increased services management for the integration scenarios. And that's it. Any questions? Oh, is mic on? Oh, there it is.
Hello. Yeah, I have a question. You did the comparison of the memory usage, and what about CPU and network when you did this?
We simplified the network one in that Apache benchmark, so that's the request per second. If I, were to if I get to a one of my architecture diagrams. The Apache benchmark probably follows about 6 of those lines on that particular one from outside to in, and it goes all the way in through the various subsystems, and container to container communication is occurring, etc., or VM to VM, and IP tables is happening. So it's actually a good representation of the networking performance. And it's actually the most important one because in this particular thing you're hosting applications and wanting them to run fast.
What about CPU? It's much different?
It didn't look at the CPU much because there wasn't really much to say. Neither of the systems were hit with much load. They were special purpose dedicated where we told everyone, please don't bother us on this hardware while we play with it. So, and we didn't do much on there. And there's neither Kubernetes nor OpenStack has a high steady state load. So it was the only time we had load was when we were doing Apache benchmark.
Thank you.
All right, thanks. Don't cut up.